Okay, ladies and gentlemen, this is a question that was presented by me by one of my clients, and this is a physics question. It's a question very similar that she saw the first time she took the Astb-E exam for the United States Navy, United States Coast Guard, and the United States Marine Corps. This was in the mechanical comprehension section. So the question, this is very similar to what she saw. And the question states, a projectile with a mass of 5 kilograms is thrown exactly parallel to the ground from a height of 40 meters. The initial velocity of the object is 20 meters per second parallel to the ground and 0 meters per second in the vertical direction. And so there's adding some additional information. Assuming that the acceleration due to gravity is 9.8 meters per second squared, how far would the projectile travel before hitting the ground? I'm going to compute for ground contact. Just to jump right in. Alright, so what they're saying is, here's our projectile, mass of 5 kilograms, positioned here at the top. We have 40 meters of height, and they want to know how far is this thing going to travel before hitting the ground. So, boom, we have our height, which is 40 feet. We have our projectile that it's going to be thrown, and we have 40 meters here. Just to recap, 20 meters per second is what it's going to be thrown at. Its initial velocity on the x-axis and on the y-axis is going to be 0, but as it's released, it's going to be released at 20 meters per second. And we have an unknown distance that this thing is going to fall at. So I'm going to calculate how far it's going to be thrown. Okay, so one thing to notice, if we throw the rock or if we drop the rock, if we throw the rock in this direction or if we drop the rock in this direction, they're both going to hit the ground at the same time. Because gravitational pull is going to react on the objects. And weight, it's irrespective of weight either, even if it's 5. If it was 5 kilograms going that way and 1 kilogram being dropped this way, they would drop at the same speed. Alright, so that is just one note. Now, what we do is we'll call the point at the top of the cliff YO, which is the initial position, and I'm going to show you an example because we had a coordinate plane which is a y-axis and an x-axis. Just dropping vertically would move about the y-axis. So YO is the initial point, Y1 is the stop point, and YO plus Y1 equals Y, which is 40 meters. Alright. Okay, next slide. So, like I said before, the initial velocity of the object being thrown is going to be called V0, which is the initial speed. And we're going to talk about gravitational pull, which acts on the object at 9.8 meters per second squared. So, if we calculate y and how gravity reacts to the distance traveled, y, which is 40 meters, yo, which is the initial velocity, over vo, which is the initial velocity of the object being thrown, plus 1/2 of a, I'm just going to change that to g because I want that to represent gravitational pull. Alright, equals t, which represents time squared. So that's not right. This should be 40 because y represents 40 feet. Actually, I was just playing that was right. I'm sorry. So let me just back up. This represents this part of the equation. YO, which is initial point, is 0 meters, plus y, plus VO, which is initial meters per second before it goes to 20 meters per second, times time. Alright, so 0 can't be added to anything. 0 times time is going to be equal to 0. So we're just left with the 1/2 gravitational pull times time squared. Okay, so that cancels out. that cancels out, like I said, and we just left with this portion of the formula. So here's where we are now. 40 meters, which equals y, this and this canceled out, and then 1/2 at squared is left. So 40 meters equals 1/2 gravitational pull here, 9.8 times time. We don't know what time is at this point, and that's what we need to solve for. So what we do is, what we have to do in order to make this work, we're going to have to isolate the t, or the t squared. So I'm actually going to do a video on this, but both sides multiply by 2. So this way we have 80 meters and then 9.8 t squared. Alright, and then what we would do is we would have t squared, and we would, let's see, we do that, and then we have to divide both sides by 9.8, and then we would have t squared, we'd have t squared over 2y g, and then since it's t squared, in order to make it t, we have to put a square root over it, and then boom. So basically, at the end of all of this, time equals the square root of 2 times the height of the cliff divided by 9.8, which is gravitational pull, and then we should come up with 2.9, but I'm going to just isolate it, and I'm going to keep it at 2.85 seconds. So that is our time. Whether we dropped the object, the 5 kilogram object, down to the bottom, or if we threw it horizontally, both of them, if we release them at the same time, just vertical dropping or thrown horizontally, would contact the ground at 2.9 seconds, or 2.85 to be very, very specific, because we have to calculate that. So after we establish that, it takes 2.9, or I'm using 2.85 seconds in the calculator, so I will go ahead and make my adjustments here, and once I multiply that, I'm going to come up with 57 meters. So that is the answer to our question. Alright, how far would the projectile travel before hitting the ground? It would hit it at 57 meters, and that's what I would go with to calculate that. So there we have it. There's your answer. And at the end, I'm just going to put a short video in there to come back to how we understand how we got the initial formula, but it just tells you how we got from this y, which is the distance in meters from the top of the cliff to the bottom of the cliff, how we got this, how we isolated t. It works out the whole thing, but specifically you will see how all this is worked out. And there we have it, 57 meters.